Okay, in this video, we are going to solve the governing differential equation of one-dimensional laminar flow system. So first, I will write the governing differential equation. That governing differential equation is mu into d squared v by dx squared plus rho g into cos theta is equal to 0. If you are wondering how we get this particular governing differential equation, I highly recommend that you go and watch the previous video. You can demystify the process of deriving the governing differential equation. I think that deriving the governing differential equation is as important as solving the governing differential equation. You may ask this question, why do you want to solve this particular governing differential equation? We have to solve this governing differential equation so that you can extract a valuable piece of information. That information is, you can tell what is the velocity of the liquid that is flowing on an inclined plane. At any point on the inclined plane, you can tell what is the value of velocity. So before we get straight into the business of solving the governing differential equation, I would like to recapitulate the physical scenario here. The physical scenario is a liquid is flowing on an inclined plane. It can be water. Water is a very conducive example. I'm going to represent the liquid that is flowing on this inclined plane by this dashed line here. Dashed green lines, they represent the liquid that is flowing on this inclined plane. What we actually did was we reckoned a set of coordinate axes. You called this as x-axis, you called this as y-axis. And what we did was we considered a small layer, representing that by this yellow line here. The small layer, that's what you considered. That is the attention. You localized your attention on the small layer and you defined the action force that is acting on the small layer, and you defined the resisting force that is acting on the small layer, and you applied Newton's third law to equate the action and the resisting force. So I'm going to repeat this. You considered the small layer, you defined the action force acting on the small layer, you defined the resisting force that is acting on the small layer, and you applied Newton's third law in order to equate the action and the resisting force, and you were able to derive the governing differential equation. And this is the governing differential equation. That is mu into d squared v by dx squared plus rho g into cos theta is equal to 0. Now what are the components of this governing differential equation? This mu here represents the coefficient of viscosity, and v, the dependent variable here, that represents the velocity of the liquid at any point, and that is measured from the y-axis. That is measured from the x-axis here. So you can tell what is the velocity at this point, you can tell what is the velocity at this point, you can tell what is the velocity at this point, you can tell what is the velocity at these points. So it is a function of x, and the x being reckoned in this fashion. Rho here is the density, g is acceleration due to gravity, and theta is the angle at which the inclined plane is actually inclined. So before we go to the first step of solving the governing differential equation, there is one more thing that we have to complete. That is, we have to define the boundary conditions. So what are the boundary conditions? So the first boundary condition is the value of velocity at this particular point. You know what is the value of velocity at this particular point? It is 0. So velocity at the point L, because this distance is L, velocity at this point L is going to be 0. Why it is 0? The reason why it is 0 is because the water molecules, it can be any liquid, they cling on to the surface. They sort of get attracted to the surface, and that is the reason why the velocity at this particular region, it is going to be 0. And as you gradually progress in the upward direction, the velocity actually keeps on increasing. And if you consider two layers, one at the very top and one just beneath the top layer, I'm going to represent that by blue. So the red layer, which is at the very top, and the blue layer, which is just beneath the red. If the value of velocity of the liquid at the very top, it is v1. Let us say that the value of velocity at the very top layer, let us say that it is v1, and the value of velocity just beneath that layer, it is v2. Then v1 difference v2 is going to be very small. It is vanishingly small, infinitesimally small, that it is almost zero. So you can immediately write the second boundary condition. That boundary condition is dv by dx. The change in velocity, the numerator, is going to be 0 at x is equal to 0. So that is the second boundary condition. So before we get to the first step of solving the governing differential equation, I have to tell you that the velocity at the point x is equal to L, that is at this particular region, it is going to be 0, and dv by dx, a rate of change of velocity at the point x is equal to 0, that is going to be 0, because the velocity gradually increases as you progress towards the top surface, and the velocity at the very top, that is indicated by this red here, and the layer just beneath the red, right, which is represented by blue here, v1 difference v2, it is going to be vanishingly small. You cannot ask why that happens, because that is the way the universe works. So it is going to be very small, vanishingly small, that dv by dx at x is equal to 0 is going to be 0. Okay, now we are going to solve the governing differential equation by following a sequence of steps. The first step is to assume a trial solution. So what is the trial solution that you are going to assume? Well, it is v of x is equal to a0 plus a1x plus a2x squared. Well, if you know the value of a0, a1 and a2, you can tell what is the velocity. At any position of x, you can tell what is the velocity. But you may ask me this question: how do you actually get this particular trial solution? How do we get this particular trial solution? So if you look at this governing differential equation, mu into d squared v by dx squared plus rho g cos theta is equal to 0. What you have to do is you have to integrate this governing differential equation 2 times. So integrate the governing differential equation twice. What is that you will be getting if you integrate this governing differential equation 2 times? The equation that you are going to get is v of x is equal to a0 plus a1x plus a2x squared. So that is the equation that you will be getting if you integrate this governing differential equation 2 times. So you will not be getting directly in that form, but at least the form of that equation, if you integrate it 2 times, that is going to be like a0 plus a1x plus a2x squared. In the first video of how to solve the differential equation of a cantilever bar subjected to uniformly distributed axial load, I have explained how do you get this particular trial solution. It's not a big deal, but you can still watch that video and you can wrap your mind around that particular concept. So all we now need to do is we have to get the values of a0, a1 and a2. So let us do the second step. So what is the second step? Second step is to apply the boundary conditions. So what is the first boundary condition? Well, we know what is the first boundary condition. When a liquid is flowing on an inclined plane, the velocity at this particular point is going to be 0. So velocity v at the point x is equal to L is going to be 0. Let us apply this particular boundary condition on this trial solution. So what is that you will be getting? When you say that the velocity is 0, this term should become 0. So that should become 0 is equal to a0 plus a1. Instead of x, we have to put L because x is any arbitrary location. We are talking about the location at x is equal to L. So it is a1L plus a2L square. Maybe you can call this as equation number 1. So what is the second boundary condition? The second boundary condition is saying that dv by dx at x is equal to 0 is equal to 0. So that is the second boundary condition. So if you apply the second boundary condition, you have to find what is dv by dx. Let us first find what is dv by dx. What is dv by dx? Well, you have to find dv by dx. What is, if you integrate if you differentiate a0, is going to be 0. So I will write differentiation of a0 is 0 with respect to x. And if you differentiate a1x with respect to x, you will be getting a1. And if you differentiate a2x squared with respect to x, you will be getting 2a2x. And if you apply the boundary condition, which is dv by dx at x is equal to 0 is equal to 0, what happens is dv by dx, this term should become 0 is equal to a1, and this term x should become 0. So a1 plus 0, that should immediately give us the value of a1 as 0. Maybe I can call this as equation number 2. What I'm going to do is look at equation number 1 and look at equation number 2. I get the value of a1 as 0. In equation number 1, if I put the value of a1 as 0, I can immediately get the value of a0 in terms of a2. So that is the trick that we are going to pull here. I'm immediately going to substitute the value of a1 as 0 in this particular first equation. So in this equation, what I'm going to do is I'm going to substitute the value of a1 as 0 because that's what we got by applying the second boundary condition. So substitute the value of a1 as 0, you can immediately get to the value of a0. So what is the value of a0? The value of a0 is equal to, if you take this term and throw it on the left hand side, what is that you are going to get is a0 is equal to minus a2l squared. Well, I got the value of a0. So by applying the second step, which is by applying the boundary conditions, that's our second step, I am able to get the value of a1, and I'm also able to get the value of a0 in terms of a2. Now all I have to do is I have to modify my trial solution. I have to simplify my first step, the trial solution. So you look at this trial solution that we have the first step. What I'm going to do is I'm going to modify this trial solution. I can write the value of a0 in terms of a2. I can substitute the value of a1 which has become 0. So I'm going to modify my trial solution. That will be my third step. So my third step here is to modify my trial solution. So step number 3, I'm going to modify my trial solution so that the mathematics becomes very conducive for me. So modify the first step, or I can say modify the trial solution. So if you modify the trial solution, the modified trial solution is v of x is equal to a0. Now I know the value of a0. It is minus a2l squared. Here it is minus a2l squared. So it is v of x is equal to a0, which is minus a2l squared, plus a1x, that is going to be 0, plus a2x squared. So I can rewrite this equation as v of x is equal to a2 is common, I can take it outside into x squared minus L squared. So all I need to do is I need to get the value of a2. If I get this value of a2, I can tell what is the value of velocity. So I'm going to do my fourth step. Fourth step is find d square v by dx square. That is going to be our fourth step. You may ask me this question, how do you get this step number 4? Well, you look at the governing differential equation. The governing differential equation demands the value of d squared v by dx squared, and that is the reason why we have to find d squared v by dx squared. So let us find d squared v by dx squared, and I'm going to substitute the value of d squared v by dx squared here. I'm going to substitute the value of d squared v by dx squared in order to get my last constant. In order to get the value of a2, I'm going to substitute the value of d squared v by dx squared in this here. So let me find d squared v by dx squared. That is easy. So what is d squared v by dx squared? Well, you have to differentiate this particular equation 2 times, or alternatively you can differentiate the trial solution 2 times. If you differentiate a0 2 times, it becomes 0. If you differentiate a1x 2 times, it becomes 0. If you differentiate a2x squared 2 times, one time differentiation is going to give you the value of 2a2x. 2 times differentiation, it is going to give you the value of as 2a2. So if you differentiate this equation 2 times, all you are going to end up with is 2a2. I got d squared v by dx squared. That is step number 4. So what is step number 5? Step number 5 is substitute. By this time you would have predicted, substitute d squared v by dx squared in the governing differential equation. So what is our governing differential equation? Well, you know that it is mu into d squared v by dx squared plus rho g cos theta is equal to 0. That is our governing differential equation. And you are going to substitute the value of d squared v by dx squared, and you are going to put that value here. And we know what is the value of d squared v by dx squared. It is 2a2. So when you substitute, it becomes mu into, instead of d squared v by dx squared, it is 2a2 plus rho g into cos theta is equal to 0. You can immediately get the value of a2. a2 is equal to minus rho g cos theta whole divided by 2 mu. I'm sorry. I just got a bit excited. I will erase this. Okay. So it's whole divided by 2 mu. So that is the value of a2. Now let me have a look at my modified trial solution. My modified trial solution is a2. This is the modified trial solution. All I need to know is the value of a2, and now I have got the value of a2, which means I have got the value of velocity. I can now tell, without having to measure practically, what is the value of velocity at any point, at any arbitrary location of x. I can tell what is the value of velocity. So here we go. The next step, substitute, which is step number 6, you may wish to call. Substitute a2 in the modified trial solution. So here we go. Our modified trial solution is v of x is equal to a2 into x square minus L square. Now we know the value of a2, which is minus rho g cos theta whole divided by 2 mu. So that becomes minus rho g cos theta whole divided by 2 mu into x square minus L square. So alternatively, I can write this equation as rho g cos theta whole divided by 2 mu into L square minus x square. I have kind of retracted a positive sign here, so that is the reason. So that is the solution to this problem. Now we have to interpret the solution. We have to interpret the solution. Without interpreting the solution, it is not complete. So let us delve deeper into interpreting the solution.